In this chapter, we will expand the topic of the Kalman filter in two aspects. The first is linearization, and the second one is sensor fusion. But first, from the previous episodes, what we want to do is to solve the linearity problem or the linearity assumption in the Kalman filter. What do I mean? As we saw previously, although the Kalman filter is a great filter, it has the linear assumption. And the linear assumption is expressed in two ways. The first is the F matrix, the matrix that transfers us from the current state to the next state. This matrix represents a linear transformation between the two states. What does this mean? That the present state can be expressed only, and this is important, as a linear transformation of the previous state. Now, we have seen in the last chapter linear models such as constant velocity and even constant acceleration. But what happens when the model is slightly more complex? If I want, for example, to describe even a very simple circular motion, I need to use the sine and cosine functions. Both are nonlinear functions. The naive Kalman filter cannot describe a circular motion. Hence, it cannot describe right or left turn in our vehicle. The other linear assumption has to do with the H matrix, the matrix that transfers us from the state space to the sensor space. For example, assume that my state space is 2D position and velocity, px, py, vx, and vy. And I have a sensor that measures only the position px, py. Wonderful. Why? Because this sensor, px and py, has a linear transformation from the state space to the sensor space. In fact, I can use any linear transformation of x and y, for example, 2x plus 4y. But what happens when I have a sensor that doesn't measure a linear transformation of the state space? For example, what happens if I have a sensor that measures the square root of x squared plus y squared, the distance, okay? In this case, I cannot use the H matrix. What can we do? The extended Kalman filter says the following thing. If your f or h function is nonlinear, find a linear approximation of this function and use it. And now the question becomes, which linear function behave the closest to the original function? This will give us the answer, and this is in fact the extended Kalman filter. The fact that this method even works is very strange. Why? Because a linear approximation of an arbitrary function is tangent to the function only in one point. Nevertheless, this method works. And in this chapter, we will cover both the linear mathematics, Taylor series, Jacobians, etc., and how to apply those mathematical principles into the extended Kalman filter.